Good day, everyone, and welcome to today's webinar on using JTAG boundary scan embedded firmware for built-in self-test. We're going to wait for maybe another minute or so. We still got a bunch of attendees in the process of dialing into the webinar. So give us a minute and we'll get started. All right, Michael, looks like we've got a bunch of folks that just got online, so let us begin. And again, good day, everybody. My name is Alan Squigna, and I'm your host for the day, and I look after your business development for assets, ScanWorks Embedded Diagnostics, also known as SED product portfolio. And today we got a real treat for you. Michael Johnson is going to do a deep dive, with a presentation and demonstration of this, technology. But before we get started, a few housekeeping items. We're going to last about 40 minutes here, give or take. Throughout the webinar, you've got the ability to submit text questions right down in your right-hand side of your control panel, and questions for the presenter, and we'll be collecting those. And at the end of the session, we'll have an interactive Q&A with Michael, right? So you can get your questions answered. As well, sprinkled throughout the presentation, there are going to be some polling questions, right, to kind of mix things up a little bit. So please be prepared to participate in those as they show up. You also have access to the PDF, a copy of today's presentation, right, in the handout section of the control panel. So without much further ado, I'm going to hand over to Michael Johnson, our presenter. He is the product manager for the assets SED for test product line. And Michael also serves as the applications engineering support manager for Asset Intertech. And Michael makes the strategic decisions necessary to ensure that SED for test meets our customers' expectations and allows Asset to grow as a business. So over to you, Michael.
Hey, thank you very much, Alan. I really appreciate that introduction. So hello all, and thank you for attending this webinar. I hope that you find it informative. I'll leave some time for questions at the end of the webinar, and I'll also make my contact information available for questions or discussion outside of this webinar. So this is the agenda that we'll follow. First, I'll provide an overview of the JTAG boundary scan technology. From there, I'll provide a definition of embedded JTAG boundary scan, or what Asset calls ScanWorks Embedded Diagnostics for Test. Next, I'll provide an overview of how the technology is used. Once I conclude with the overview, I'll discuss the actions supported by SED for Test. Then I'll discuss the value of SED for Test as a powerful application of the JTAG boundary scan technology. Next, I've prepared a demonstration using the SED for Test technology, so I think you'll really get a treat out of that. Then I'll discuss the amount of onboard resources that are used and necessary for an SED for Test implementation, and then we'll wrap up with a few concluding remarks, and we'll open it up for any questions. So JTAG boundary scan overview. JTAG boundary scan is a static, vector-based test technology implemented through on-chip embedded instruments within commercial silicon. The graphic on the right depicts a JTAG boundary scan implementation within the chip. The various registers and the tap controllers within the chip facilitate the movement of the static text vectors in and out of the chip. JTAG boundary scan performs shorts, opens, stuck at fault testing on printed circuit boards with diagnostics down to the net and to the pin level. By shifting static test vector patterns between boundary scan devices on a PCB, faults can be detected and diagnosed. These boundary scan vectors are usable throughout the entire life cycle of a product. Again, whether those vectors are developed on a benchtop application, they can be used in PCB production or even doing PCB repair. And boundary scan is a proven, mature test and programming technology. JTAG boundary scan has been in existence since 1990. It's been implemented within ICs used on PCBs across the spectrum of electronic industries and throughout many devices. So, ScanWorks embedded diagnostics for test. Let's give a brief overview again of just how JTAG boundary scan is used. JTAG boundary scan is typically used locally for PC test development, production, and system debug. So in a typical application, an external PC uses a dedicated hardware controller to test and program PCBs in development, manufacturing, or to perform debug on a benchtop. The JTAG boundary scan tests are again created on a PC, which is connected to a hardware controller. That hardware controller is then connected to a PCB, which is the target for our JTAG boundary scan test. As you can see in this graphic here, we have a PC, we have our controller, and our target PCB. However, since JTAG boundary scan is software on the PC can leverage the on-chip embedded logic. It's possible to port the JTAG boundary scan software onto the PCB itself. If the PCB has an FPGA, an SoC, or a service processor. So this is where ScanWorks for embedded diagnostics for tests comes into play. SED for tests eliminates the need for hardware, cables, and fixturing in order to run JTAG boundary scan testing on a PCB. So as you can see, there's no need for a computer and there's no need for a hardware controller because ScanWorks and the JTAG test is embedded on the PC. So with SED for test, we create a dynamic and really powerful remote JTAG boundary scan test and programming application. So Alan, I think this is a good time for me to pause and I'll hand it over to you for our first poll question.
All right. Hey, thank you, Michael. Yeah, good idea. Let's just maybe get a little bit of the lay of the land on our audience here. So the first poll question is, are you currently using boundary scan for any benchtop-based debug? So a yes or no question. Yeah, so let's give the audience a minute to answer, and then we'll tally up the responses and see how many folks are actually working with on a day-by-day basis with boundary scan on the benchtop. All righty. About 3/4 of the audience has voted so far, so we'll give it another moment to close out. Okay, going once, going twice. All righty, let's close the poll and see what the results are so far. Let's share the data with everybody. Yeah, okay. It looks like most of the audience, 85% of the audience, is actually working with boundary scan on a day-by-day basis, on benchtop platforms, and a small percentage, 15%, said no. All right, very informative. Back to you, Michael.
All right, thank you, Alan. So just a formal definition of ScanWorks Embedded Diagnostics, or what we call SED for test. ScanWorks Embedded Diagnostics, or again, SED for test, is a tool strategy that supports JTAG, boundary scan testing, and device programming capabilities embedded directly on a PC. So as you can imagine from the overview given on the previous slide, SED for test is applicable to a variety of industries and technologies where in situ, real-time diagnostic data collection is valuable. So whether that's defense, communications, etc., this implementation is a very powerful use of the JTAG boundary scan technology. So the SED for test actions that are supported, for those of you that have used ScanWorks, you're familiar with the actions that I've presented here on this slide, but a wide range of actions are supported through the SED for test. Scan path verify, which is the test action that we use to just test and validate the boundary scan devices on the board. The interconnect action, which is the structural testing action incorporated into ScanWorks, and that's where we can check the PCB for shorts, opens, stuck at faults, and diagnose any of those faults down to the device and to the net and pin level. Memory access verify, which is where we do structural and functional testing of memory devices. There's a variety of programming options, whether you are configuring FPGAs or CPLDs using SVF or Staple. For any flash devices that are on your PCB, whether those are NOR, NAND, SPI, or I2C, the flash action is available. And if there's any discrete I/O that need to be controlled on the PCB as well. So all of these actions are available for use within the SED for test technology. So let's talk about some of the value propositions of SED for test. Number one, again, SED for test can be executed remotely and in situ with diagnostic data gathered in real time. SED for test can be executed as part of a built-in self-test algorithm or a power-on self-test algorithm. It could be used for system audits and for operational measurements. SED for test only requires that the PCB powers up, so there's no requirement for the PCB to be operational, which is powerful. So again, if the device is not functioning, again, as long as there's power and the boundary scan devices are operational, you can still implement SED for test on your PCB. So that means SED for test is completely out of band. It's not dependent upon the functionality of the PCB. And SED for test can be used in implementing what's known as system JTAG. So if you have a backplane with several PCBs plugged into the backplane, you can run a boundary scan through that complex multi-board system and gather diagnostic results. So SED for test can be used in a variety of different applications. More value propositions for SED for test. SED for test provides a level of diagnostic granularity not usually found via in-system functional tests. So with SED for test, you may have a PCB in an environmental chamber going through temperature or vibration or stress testing. If you're running SED for test on that PCB, you can be gathering real-time data in somewhat of a functional and environmental environment. Also, you can analyze the effects of aging over time on the PCB as well with SED for test. The same ScanWorks PCB tests used for production can be reused in situ and during repair. The data that you collect during the device, during SED for test operation, that can be uploaded to a benchtop system for diagnostic processing and reporting. And one really important aspect of SED for test is that it can help address intermittent faults, or what's known as no fault found issues. So for instance, structural faults may be detected in the field on a PCB. Maybe that triggers an alarm. That PCB is shut down for that reason. But when the PCB or the module is returned to the depot and diagnostics are run on it, there's no fault found. Well, you know, that's a real problem, and that can decrease PCB availability and lead to poor reliability. But if SED for test is running on that PCB, if there's a fault, that data is automatically captured. So even if the PCB displays no fault found when it's returned to the depot, you have the information on the fault that was captured while the PCB was out in the field. So again, a very powerful application and use of SED for test. So Alan, I think this is another good time to pause, and I'll let you ask our second poll question. So Alan, I'll turn it over to you.
All right, thank you, Michael. Yeah, you mentioned the NFF issue. We want to get a feeling for folks that may have experienced, something of that nature, right, in terms of their product line. Most everybody on the webinar has had some experience with boundary scan, but this question regards, have you ever experienced intermittent product failures that you suspected were due to structural faults? So let's get a feel for that. We're gonna, it's a yes or no question. We're gonna collect the responses. And we're up at around 83% of 84% of the attendees have responded. So let's give the other folks a chance to weigh in. Appreciate your input, everyone. All righty. All right, so we got to 87% voted. So let's close out the poll now and then share the results. Yeah, so all right, yeah, so as we somewhat suspected, right? I mean, this is an endemic issue, you know, within high availability systems in particular, right? Intermittent faults are a big issue, lead to enormous NFF cost. And it looks like 96% of you actually have had some experience, in that respect. So thanks everybody for weighing in, and we'll close out the poll and allow you to resume, Michael.
All right, thanks, Alan. So I've prepared a demonstration, and so I won't go through it live here. I'll actually recorded it for you, so you'll get an opportunity to sit back and watch a recording of an SCD for test demonstration. But before I begin the recording, I'd like to just kind of give you a little background on the hardware that's used for the demonstration. So for the demonstration, I'll be using an Altera Cyclone 5 SoC. It's got a dual arm Cortex A9, which is a system on, so that makes it a system on chip because it's combined with an FPGA. The operating system that is running within the Cyclone 5 is VxWorks. And so for the demonstration, I'm going to use it as my host, where I will embed ScanWorks, or what's known as our ScanWorks SCD player. And that embedded player will run the actions that I embed into the SoC. And so that's what you'll see during the presentation. And the actions, the results from the actions that I'll run during the demonstration, I'll be able to capture those, and we'll store those off, and we'll be able to analyze the diagnostic results. So that's the first half of the hardware that we'll use for the demonstration. And the target for the boundary scan test is a ScanLite 2. And most of you guys who have been to our training classes, you're familiar with the ScanLite 2 demonstration board that Asset produces. The device, or the board, has 3 JTAG boundary scannable devices. Again, I said it's going to be the target for our boundary scan test actions that will run using the SCD player. And the ScanLite 2 has a number of fault insertion switches, which you can see on the graphic. And during the demonstration, I'll be flipping some of those faults, or some of those switches, to create faults, so you can see the diagnostic capabilities of SCD for test. So just wanted to give you a little background on the hardware that I'll be using for the demonstration. And just to kind of walk you through the process that I'll be following in the demonstration. So you can see up in the top right-hand corner, there's my PC with ScanWorks installed. So the first step that I'll do in the demonstration, I'll access the SCD host. Again, that's our Cyclone 5 SoC. I'll access it using an Ethernet connection, and then I'll go through and create the necessary file structure within the Cyclone 5. For those of you that are familiar with ScanWorks, when you start any kind of project, you create a project folder, you create a design folder, and then you create actions. Well, essentially, since we are embedding ScanWorks on the Cyclone 5, it requires the same file structure. So I'll create that file structure, and you'll see that as part of the demonstration. So once I have the file structure created, I'll upload the SCD player that I just mentioned, which makes it possible for us to run ScanWorks on this SoC. I'll also upload some files, action files, that are necessary for me to be able to run the various actions that I'll run during the demonstration. And so I'll do all that via an Ethernet connection. And so once that's done, again, we'll have ScanWorks embedded on the Cyclone 5 SoC, and we'll be ready to continue on with the demonstration. And then from that point, I'll have a serial connection from my PC, where I'll be just issuing commands to run various actions, again, using the embedded ScanWorks on the SoC, okay? So even though you'll see me entering those commands in a command window, I just want to stress this point. is that once you have ScanWorks embedded on the SoC in this case, and you have the necessary action files embedded within the SoC as well, the actions, although I'm running them from a command line interface, those could easily be automated with some type of script or program that just runs, again, just strictly on the SoC or your service processor or whatever you're using for your SED host. So the commands don't need to be issued from a PC, don't need to be issued from ScanWorks. ScanWorks is totally running and embedded on the SoC, and the commands, again, can be issued directly within the SoC as well. So just wanted to drive that point home. So again, during the demonstration, I'll be issuing commands from a command prompt. And again, the target is the scan light. So we'll run some test actions, we'll get some passing results, and we'll get some failing results as well. So again, you'll see all this during the recorded demonstration. And then at the end, for the faults that we will have detected using SED for test, we'll upload those back to the ScanWorks station, and we'll perform some diagnostics on that to actually interpret what the faults are. So again, during the demonstration, you'll see that I'll be flipping a number of switches. The first switch that I'll flip in the demonstration is the switch number 5, which creates a TDO, TDI shift fault. So that will break our scan chain on the board. There's a second switch, switch 2, that I'll flip, which will create a IO short. And then switch 10, I'll create a bridging fault on one of the address lines going to the memory device on our board. So I'll run 3 test actions during the demonstration. And again, you can see how SED for test can analyze those faults that we'll detect, and we'll send those results back to the ScanWorks station for further analysis. So let's go on to the demonstration, but hopefully you can see, even before we jump to the demonstration, that SED for test has a broad application across many industries where JTAG boundary scan tests are required, and it can really provide valuable diagnostic data, right at the point of the failure on the PCB. And so with that, I will start the presentation. So let me switch over, or demonstration, I'm sorry. So let me switch over to the recording, and we will get started. Okay, let's get started. So I've already done a little pre-work to get us ready for the demonstration. So I'll go over what I've already done, and then we'll continue from there. So I'll be using FileZilla to upload files to the Cyclone 5 SoC. And those files that I'll be uploading are the SED for test, or the ScanWorks runtime files for the different action types that I'll be demonstrating. And then there's also what we call the SED player, which actually makes running the actions possible on the SoC. So I'll show you how those can be uploaded. Also, here on the right hand side, I have a connection to the Cyclone 5 SoC, and as you can see, I've created a ScanWorks projects, design, and action hierarchy. So those of you that are familiar with ScanWorks, when you first start off, you create a project folder, and then you create a design folder, and then the next thing you do is you create actions. Well, since we'll be running ScanWorks on the SoC, the same project structure is required. So I've already created that. So the project is called SED demonstration. The design is action demonstration. And the 3 actions that I'll be demonstrating today are the scan path verify, or SPV1. I'll be demonstrating an interconnect action, so I've named that folder interconnect action 1, and I'll be demonstrating the memory access verify action, and so that folder is MAV1, or MAV1. And you can see that each action has a results folder. So once I run the actions, the results will go in those folders, and then we'll take the next step in looking at the results, or we'll diagnose those results. So you'll see that here in the presentation. So the first thing that I'm going to do is to upload, again, what we call the SED player. And the SCD player makes it possible for us to run the ScanWorks actions on the Cyclone 5 SoC. So I'll go ahead and I'll upload that. And I'm just going to stick that in the root directory. So I'll go up here to the top. And you can see here what's in the directory already. There's a players folder and there's a projects folder. So I'm just going to put the SCD player just right in the root directory. So I have that file here on my local PC. So let me navigate to that particular folder. So it's in a folder called SCD player. So I'll open that up and you can see I've got an SCD player file right here. So I'm again going to upload that to the Cyclone 5 SoC. So it's just real simple. I'll just select the file and click upload. And we can see that the file is uploaded to the Cyclone 5 SoC. All right, so I've got that. So the next thing I need to do is for each one of these action types, there are certain files that are required that need to be in these folders that allow the actions to run. So I'm going to upload the necessary files to each one of these folders. So I'll just start out with the SPV folder. So I'll click on that. You can see right now there's nothing in the folder. And again, we have the results folder, which is beneath the SPV one. So I'm going to upload again the necessary files for the SPV action to run. So I have those files here on my local PC. So I'll actually just copy them from my ScanWorks installation. So here is my SPV1 folder in my ScanWorks installation. Again, there's a couple of files that I'll need, so let me find those files. The first file that I need is called SPV1 gen. So I've got that file. I'll highlight it. And I need the SPV1.eie file. So I've selected both of those files and I'll just upload those files. So now those files are resident on the Cyclone 5 SoC. Okay, so those are the two files that I need to be able to run a ScanWorks embedded test, ScanWorks embedded diagnostic test action on the Cyclone 5 SoC. Okay, so now let's go to interconnect. So I'll click on interconnect. As you can see, there are no files in the interconnect folder, and we've got the results folder that's sitting under the interconnect folder. So there are a couple files that I need to upload to the interconnect folder. So I have those files. Again, they're right in my ScanWorks installation on my computer. So I'll go to the interconnect folder. Now the files that I need for the interconnect, actually there are three files that I need. So let me scroll down here. So the first file, it's the interconnect underscore EIE gen. So I have that file. So I'll select that one. There's an interconnect one underscore EIE.apl file. So I need that file. And then there's one more file that I need. It's the interconnect one.eie. So I have the three files that I need to upload to the Cyclone 5 to be able to run an interconnect action. So I'll simply upload those files. And now those files are, or a copy of those files, are now on the Cyclone 5 SoC. Okay, and same thing for our memory test. If we want to run a MAV test, there are a couple of files that I need to copy over. So I'll copy those from my ScanWorks installation. So I'll go to the MAV folder on my ScanWorks installation. And there are two files that I need for a MAV action. And that is the MAV MBS and the MAV EIE. All right, so I've got those selected and I'll upload those. Okay, so I've got all of the necessary files. I've got the SCD player and I have each one of the files in the proper location in the action folders to be able to run these actions. So I've got the files for the SPV, I have the files for the MAV, and I've got the files for the interconnect action. Okay, so at this point, we're ready to go. So in order to be able to run those files, I have a serial connection into the Cyclone 5 SoC. And you can see the operating system that is on the Cyclone 5 is VxWorks. Okay, so I've established this serial connection. And so what I'll be able to do is write or type commands to run a scan path action, or to run an interconnect action, or to run a memory access verify action. So I'll be manually inputting these commands into this window. And again, the tool that I'm using is a TerraTerm to have this serial connection into the SoC. So I have the commands actually cut and, I'm sorry, I've got them already typed out in another window. So I can just cut and paste those commands, so you don't have to watch me sit here and type the commands. But I will cut and paste those commands into the window, and I'll actually be able to run the actions. So in a live application for SED, this could all easily be automated through some kind of script or just through some kind of program. But just for the sake of the demonstration, you'll see me just enter the commands here just in a command window. Okay. So first thing that we always do is run a scan path test. So I will run a scan path test. So again, I've got the commands already copied, so I'll copy those here, and I will just paste it in this window so you can see the command. So there's the command there, and it's going to use the spv1.gen file. So let me run that. And before I do that, let me make sure all of the switches are properly set on my scan light, which is the target for these tests. So I'll go ahead and run that test. And as you can see, the action passed. Okay, that's great, because I have all of the switches set in the proper location, and so there was no break in the TDI TDO path. So that test passed. So let's go take a look at the results folder here. So we can see that there was a log created. Actually, there was a couple files created, but we'll just look at the log file. So this has the results of the scan path verify test. So what I'll do now is I'll just upload those files back to my ScanWorks installation, and we'll just take a look at the results. So just to make things easy, I'll just put them in the scan path file or scan path folder. So there's my scan path folder. So I'll select that SPV1 log. We'll download that, and the file is downloaded. Now let me just do a refresh so we can see it. So there's my SPV1 log from the scan path test that I just ran against the ScanLite 2. So we can just do an open and just look at the results. And those of you that are familiar with ScanWorks, you're accustomed to seeing these types of results where ScanWorks does a check of all the registers of the boundary scan devices, just performs the validation of all the registers, whether that's the bypass register, the ID code register. We do a boundary scan length test. So run several tests that are all part of the SPV test. Okay, so we can see that the result of the test is that the test passed, which is what we see in the window here. The test passed. Okay, so now I'm going to flip the switch, which will break the TDI TDO shift path, and I'm going to run the test again. So again, I'm just doing all of this through just the command line, but again, these tests could easily be automated and just run on the SoC on your board or service processor on your board just at different intervals. So I will run this test again, and we can see that the test action failed. So I'm going to go back over to FileZilla, and I'll just do a refresh. And so here's my new SPV log, SPV1 log. So I'll select that, and I'll just download that file. Now we'll overwrite the existing file, so that's okay because we ran the test again and we want to look at the new data. And so if I just simply open that file, we can see that, okay, there is a fault where we passed the ID code test for one device, but the ID code for the other two devices failed. And so this is the result that we would expect with breaking the TDI, TDO shift path on the ScanLite 2. And for those of you that have attended the training classes and you've done this before, just connected to an asset controller, this is what you've seen in the past. But again, we're just running these actions, resident right on the SoC. Okay? So we've run our scan path test. We've got a passing result and we've got a failing result. Okay, so let's move on. Let's run an interconnect test. All right, so for the interconnect test, and before I do that, let me make sure I've got all my switches set, because we're going to create a interconnect fault. I believe the fault that we're going to create is a short between two I/O on the board. So let's go ahead and let's run that test. So again, I'm going to copy the command. I've got it again just in another window, so you don't have to sit here and watch me type that command. But this is the command that will run the interconnect action. But before we do that, let's go over here so you can see there's no results in the results folder at this time prior to running the action. So I'll go ahead and run the action. Oh, said the action failed. And you know why? Because I didn't set the TDI TDO switch back, so it caught that failure. Okay, good real-time example. So now that I have all of the switches set on my board, let's try to run that again. All right, so I run the interconnect action and we can see that the interconnect action passed. So let's do a refresh so we can see the new files. And there's a log file, interconnect 1 log file. So I'm going to bring that back over to my scan workstation so we can just take a look at it. And I'll just put it in the interconnect folder here. So I'll select that file, I'll download that, and there's the log file. And let's just open that. So we open that file, it says test completed successfully, so there's no shorts or opens on the board. Fantastic. Okay, let's close that. And so now I will create a fault. And so this is an actual I/O fault. So we're just creating a short on the board. Okay, so I flipped switch number 2. And I'll just cut and paste the command back in the window here. We'll run that. And you can see it says action failed. Okay. So let's just do a refresh so we've got the latest and greatest files. So with the interconnect action, when a failure is detected, not only do we get a log file, we get a file called a DTF, or interconnect 1, or whatever your action name is, with the .dtf extension. So this file, the DTF file, has the failure information. And so we're going to copy that information, or copy these two files. We'll copy those back over to the interconnect folder on my ScanWorks installation. So we'll download those. So I already have a log file, so we'll just overwrite that existing log file. And so now we have the new log file, and we have a DTF file. Okay, so we'll take a little different step here. We need to diagnose the actual fault. What took place when the DTF or when the interconnect action was run? So there's a command in ScanWorks. Some of you may be aware of it. You may have seen it. It's called swdiagnose. So we're going to run the swdiagnose command on the DTF file, and so that will tell us exactly what the fault was, what occurred. And so we'll run that, and we'll put the results in this interconnect 1 folder that I've created. So right now you can see there's no files in the interconnect 1 folder, but once I run the swdiagnose, we'll see a .res file appear in this folder, and it's a text file, so we can open up and see what the actual failure was. Okay, so to do that, I actually have a command window here, so we'll just run that. So this is just a regular Windows DOS command that will run. So I've got that command copied in another window. So again, you don't have to sit here and watch me type these commands. Oh, that is the wrong command here. So let me just back up of that one. And we'll run the right command. We'll run the one with the swdiagnose. So, as I said, we'll run swdiagnose. We'll run it against the interconnect1.dtf file, and we'll send those results to the folder that I just showed you a second ago, the SED results folder with the interconnect1 folder. So let's go ahead and run the swdiagnose. So you can see that it's running. And it's complete. Okay. So, as I said a minute ago, this folder was empty, but now we have what's called an interconnect1.res file. So let's just open up that file, or I can just double click it, bring it up in an editor, and we can see that we've got a diagnosis of the failure. Failure detected at node test switch 2_B. Here are the failing pins, and ScanWorks diagnosis. Read pin U8-48 failed. Okay, great. So again, all of this is just being run right on the SoC. Okay, let's go back up a level, and we'll run our math tests. But right now you can see there's nothing in the math folder. So we'll have some results there in a moment. So let me go here to our Terraterm window, and so now I'll run the math test using the SED player. So again, I've got those commands copied in another window, and I will paste that. But before I do, let me make sure I've got all of my switches set correctly. So we should get a passing result. Okay, so we've got a passing result. So our math test passed. So let's go over here. I'll just do a refresh. I'll look in the math folder. Let's just do a refresh again. And there's our log file for our memory test. And so I'm going to copy that over to my ScanWorks installation just so we can take a look at it. There's the log file. I'll open that up, and we can see that the math test passed. Okay, fantastic. So now what I'll do is I'll create a memory fault, and this is creating a fault by flipping the switch. It's creating a fault on one of the address lines going to the SRAM on the Scanlight 2. Okay, so I will run that test action again using the SED player. You can see that we've got a failed result. Let's do a refresh on the math folder. You can see that we have a .dtf file. So similar to the interconnect, when there's a math failure, ScanWorks will generate the file with the action name and the extension .tdf. So let's copy that over so we can take a look at it. We'll overwrite the log file, that's okay. And now we have our mav1.dtf. Okay, so similar to the interconnect action, we'll need to use the swdiagnose command to actually figure out what the failure is. So let me copy that, and I will paste that here in my Windows command window, and we'll run the swdiagnose. Okay, so that's complete. So now let's take a look at the failure information. So I showed you this folder before, and again, there were no files prior to running the swdiagnose, but now you can see there's a mav1.res file. So let's just open up that file, and we can see the actual failure information. So we can see that the address bit A4, we've got the node information, which is also A4, and the failing pin, which is U9 pin 1. So that's the diagnostic message that ScanWorks gave us, but we had to run the SW diagnose command in order to be able to see that. Okay, so this wraps up the demonstration, but I hope that you were able to see that by simply uploading the SED player to your SoC or to your service processor and uploading the necessary ScanWorks files that allow the actions to be run, that you can embed ScanWorks again on your SoC or on your service processor to just run completely on your board. And again, those actions can be run via script at a certain time, or you could write a program around those actions to make them run. Once the actions are run, or again, they could even be part of a power on type of situation where before your board goes out in the field, you want to run some kind of power on check, system check. You could make the ScanWorks actions part of that sequence. Once the board returns in from the field, if there were some type of failures, you could download those results like I did. You can store those in a results folder or anywhere that you'd like to store those results. And you could copy those over to your ScanWorks station, or you could just look at the logs. If they are actions that require the SW diagnose command to be run on them, you can run them again just from the command line, and you can see the actual faults. So ScanWorks for embedded diagnostics, it's a very powerful tool. So I hope I was able to convey that to you during this presentation. All right, well, thank you for viewing the demonstration. So hopefully that came across pretty clear. And if there's any questions on it, we can certainly address those at the end of the presentation here, or certainly offline if you'd like. So just a couple of subtleties that just want to make sure that you caught during the demonstration. First, there was a ScanWorks project and a design that was created to test the target. So that's certainly a prerequisite of any SED engagement. So again, there was a project and design that was created to test the ScanLight 2. And so you can see that here. I just took a little screenshot of the GUI there for the ScanWorks GUI. And the files that I transferred over to the SoC, aside from the SED player, all those files were generated during the normal ScanWorks test development process using the benchtop tool. So there's no extra effort that went into creating the .eie, the .gen, the underscore eie.gen, the underscore eie.apl, and the .mbs file. All of those files were created using the benchtop tool when you're going through the necessary ScanWorks project development, ScanWorks project design and action creation process there. So again, we just simply uploaded those to the SoC. Now, you may have noticed a number at the end of the SED player command. There was a 1, there was a 2, and there was a 3. Well, that just simply told the SED player which action it was to run. So the 1 corresponded to SPV, the 2 corresponded to interconnect, and then the 3 corresponded to the memory access verify, or the MAV action. And in this example, the operating system on the SoC was BIST, but any operating system could be used, even any RTOS or even bare metal. So again, just for this example, it was VxWorks, but it could be any operating system. So we would certainly work with you to adapt SED for test to the operating system that you have running on your particular PCB. Now, a common question that always arises is how much real estate will an SED for test implementation require in my FPGA or my processor? So here we have a FPGA SoC and we have a service processor. So for the FPGA, for implementing the resources required for the tap controller IP, it's relatively small when compared to today's FPGAs. So we're talking about less than 4,000 lookup tables and less than 75 kilobits of memory. And the action players that run on the CPU, that occupies less than 200 kilobytes of flash. So not a lot of resources are necessary on your SoC or on your service processor, again, to be able to implement SED for test. And so at this point, Alan, I think I'll pause for you to ask your final poll question.
All right, thank you, Michael. Yes, the third and final poll question is, do you have a, hold on, let me launch this first, of course. Do you have a service processor on your design capable of hosting the JTAG embedded engine? And I think that refers to the footprint, right? The resources available in terms of RAM, flash, yeah, FPGA footprint, and so on. Right, Michael?
Yes, that's correct.
Okay, so we've got three choices here: yes, no, or I don't know. And we're collecting responses here. 79% of the audience has voted. So we'll give it another moment to get it north of 90%, maybe. All right. All right, that looks good. 92% of the audience has responded. So we'll close the poll now and share the results. It looks like 50%, half of us were aware of the footprint requirements, and would SED would fit. 9% no, and 41% would probably have to check the characteristics of their design to see if it had the resources available to run the embedded engine. All right, I'll close those then, and back to you, Michael.
All right, thank you, Alan. So just in summary, SED for test embeds JTAG boundary scan test capabilities directly onto a PC. It creates a powerful built-in self-test without external hardware that can be used throughout the entire life cycle of the PCB. SED for test can be executed as part of a power-on self-test or used for system audits, all in situ with data collected in real time. The action diagnostic results can be uploaded and processed by a benchtop ScanWorks system, and it can certainly be used to address the no fault found issue that seems to be common throughout the electronics industry. So very powerful. There's more summary conclusions that I could have listed, but I list those throughout the presentation. But hopefully you are able to see that SED for test is a very powerful implementation of JTAG boundary scan, and certainly would benefit if you certainly have the real estate within an FPGA, SoC, or service processor on your board. It would certainly benefit you to take advantage of this really outstanding technology. So we have more information if you'd like on SED, our SED product offerings. We have a blog that we've written about SED. There's an ebook that you can download, and there's even another webinar that you could view. So just make note of these links and view them at your leisure, and download the ebook for further reading on this topic. I think you'll enjoy all of the content that we put together on this topic. And with that, I'll wrap up. So thank you for your time and your attention. And Alan, are there any questions from our audience that have come in during the presentation?
Yes, Michael, there sure have been. And we're running a little bit behind schedule. So thanks for everybody's attendance so far. I think we've got time for a couple of questions here. First one was, could you clarify the use of how ScanWorks fits into the SED for test strategy?
Okay, so ScanWorks is only needed for the initial boundary scan test creation and for offloading and running diagnostics on the data gathered. During the demonstration, you saw me use the SW diagnose command. So we will use that command to run and diagnose the failure data within the DTF files. So again, ScanWorks is just needed for the benchtop application, is just needed for just the initial project creation. The files that are created during that process, you saw me upload those during the demonstration. And the only thing that you would need from Asset would be the SED player, and of course customized to whatever operating system is running on your particular PCB.
All right, and here's another one for you, Michael. What is the maximum T-clock speed at which these tests can be run in order to pick up timing faults?
We've in the implementations that we've, or engagements with SED there, the T-clocks were pretty much in the range of if you were using just the Asset hardware. So it's all dependent upon the rating of your particular SoC. Again, that information can be found within the BSDL for the SoC for the FPGA fabric on it. If you're just using a service processor, that amounts to basically just kind of bit wiggling and toggling I/O to create the vector patterns. So that may tend to run just a little slower. We've seen that maybe in the 5 to 10 megahertz range, but with an SoC where you've got the embedded FPGA fabric, the T-clock rates are much higher.
Okay. All right, good. Yeah, you know what, Michael, it looks like we're out of time for answering questions. Anything else you want to cover off before we start to wrap up?
I don't think so. Again, feel free to contact me should you need any additional information for SED for Test. Again, I'll also invite you to visit our website to learn more about Asset's additional test and debug product offerings. And with that, again, thank you so much for your time, and hope everyone has a great day.
All right, and thank you, Michael. And for the audience, thanks for attending today. All right, for the other questions that came in, we'll be sure to reach out and respond, one-on-one, right? Or again, feel free to email Michael at his contact information that's up on the slide right now. And one little favor, if you could, before you exit today's webinar, when we close it up, there's a survey, right? A few questions on the back end, right? That gives us some feedback overall on the webinar and helps us to improve for the new one. So if you'd stand by and answer those questions, so we'd really appreciate it. And as a reward, you'll also get within 24 hours, an email with a link to the recorded webinar video as well. So on behalf of Asset and Michael and I, thanks very much for attending and have a great rest of your day.